All right, wonderful. This is Jean-Marc Mommsen with MarkTech Post. Super excited today to interview Joey Conway here at NVIDIA. We're going to talk about Llama Nemotron Ultra, Parakeet, and a bunch of open source models that they've put out. Joey, welcome.
Yeah, good to be here.
Excited to have you here. Super excited about all the open source models you guys have put out. Maybe you want to first introduce yourself?
Yeah, so I'm Joey Conway. Our team we do product management for some of the deep learning software at NVIDIA. So we spend time working on large language models like Nemotron and Llama Nemotron, as well as some of the text-to-speech models like Parakeet.
Okay, wonderful. And how long have you been at NVIDIA?
A little bit over 7 years.
All right, so you've been through the different a few waves.
Yeah.
Wonderful. In waves of innovation in AI. Wonderful. All right, so you guys just put out a few weeks back Llama Nemotron Ultra, which is 253 billion parameters, which, based on what I saw, what read, delivers on par performance with Llama Behemoth, Maverick, DeepSeek R1, which are about double the size. And as a result, it runs on one single 8x H100 node, which is pretty impressive. What else can you tell me about the Llama Nemotron Ultra before we talk about how? But like let's talk a little bit about the features here and why it's impressive. Furthermore.
Yeah, so we love the open source community. There's all sorts of great work happening out there. And with Llama Nemotron, we wanted to build upon what was in the community. So Llama is a great starting point. We love the work Meta's been doing there. And earlier this year, there was work around reasoning in the open community as well, too. And so as we saw a lot of that happening, we wanted to try and chime in and help out and see what we could do to improve Llama for some use cases that we felt would matter more towards enterprises or large companies. So we focused heavily on the reasoning as well as things like some of the agentic tasks like tool calling or chat. And so our goal there was to take what was in the open source community and help improve it and expand upon it and then contribute all that back.
Did you feel there were some gaps? Like, can you give one or two specific gaps that you felt that you could potentially address? You've talked about reasoning, but like maybe some enterprise agentic examples that you're like, what it failed there and it works for us, and
Yeah, I think that in like, let's say prior to January when we started this effort, there were essentially in a lot of enterprise deployments, there's this challenge of more complex queries that require essentially more thought and reflection to be able to solve. And they could be things like they might be multi-step queries, or they could involve significant calculations and using various tools to get to an outcome. And so open weight models with reasoning, there weren't very many good options at the beginning of the year. And so that's been one of the big shifts we've seen the last 4 months that we're really excited about. I think another one is that in that domain of enterprises deploying these, there's often challenges of calling the right APIs or being able to follow instructions closely around user queries. And so we also wanted to make sure that not just working on reasoning, which was exciting, but also make sure we didn't regress some of the more important use cases that they'd still need to put in production. And we also saw often when these were both solved, they were solved in two separate models. And so we wanted to try and make it as simple as possible that rather than having to deploy two models, we could do things in one model. So that was kind of the state of the world, I think, in January, February when we set out to work on this.
okay, yeah, I agree. That's a little bit my point of view as well. Okay, now we're gonna dive in a little bit to the how you guys pull this off. So there's something pretty innovative that you guys published in the paper associated with this model, which you call FFN Fusion as a key optimization. Can you talk a little bit about that? And maybe we'll start high level and then we can dive in more details as you see fit.
Yeah, and I think to set the context, the reason we are focused on this is we realized that deploying some of these best models in the world, these world-class models, the deployment footprint was quite large. And so we wanted to do our best to try and shrink it down to some of the more common GPU deployments. And so in doing that, we spent time looking through what would be good techniques or approaches to do that. And so there's one that we published called Puzzle, essentially, which is a type of neural architecture search. And what we found is that for these dense transformer models, which have been very common, especially in the Llama, like Llama 3.x family of models, we found that there was a way to essentially reduce or remove redundant attention layers. And when we did that, the FFNs or feed-forward network layers essentially lined up in kind of a sequence. And once we had them lined up, we could then work on how to fuse them. And the reason we do all that is our goal is always on the GPU to work towards parallel execution as much as possible. And so one way to do that is to take disparate compute chunks and combine them together wherever we can. And so by removing some of the redundant layers, we found opportunities to combine, essentially like merge or fuse them. And once we did that, it allowed us to do more parallel execution that previously we couldn't. And so that's just kind of an example of how we think about the challenges of running these models at scale. And what also is exciting about this technique is the larger the model, the bigger the opportunity to improve it. And so when we worked on the Ultra model, which is based off of Meta's Llama 3.1405b, we had more opportunities there to do that than we did at some of the smaller sizes.
Interesting. And yeah, I think the FFN fusion it significantly improved the throughput, right? Of the model. And you achieve great speed ups. I forgot top of mind, was it 2x or is it 8x, 4x?
Yeah, it depends on the model size. For the Ultra, I think we're in the range of 3 to 5x. And it also allowed us to, once we reduced the kind of the model size, the weights essentially, we then use less memory footprint. And so we're able to have a larger KV cache. And so for the Ultra, we were able to fit onto four H100 80 gigs, which was exciting because we're definitely within the common size of a node and even smaller. And so with that, we both had the compute speed up as well as the reduction in the memory, so we could fit larger context lengths in there. So those are both kind of two exciting outcomes from the technique.
Okay, we're gonna switch gears a little bit here. We're gonna talk about data curation, AI data, and because you guys did, I looked at your architecture to train this model and your pipeline. It's very impressive. I almost want to share my screen and show it. Maybe we'll describe it and tell me how you guys thought about this. You touched upon it a little bit at the beginning of this conversation about catering towards instruction following and making sure that doesn't degrade as you seek this goal. So let's talk a little bit about data curation, how you thought about it, and people can refer to the architecture diagram that you guys posted on your blog post, and we'll
Yeah.
link.
Yeah, perfect. I love that diagram as well. And it
Yeah.
highlights essentially the workflow because when we set out to do this, we didn't know it was possible, but we wanted to make sure, however we approached it, we could do it in the best way to open things up. So we wanted to share as much of the data we could, as much of the techniques and the tooling. We wanted it to be really transparent so people could take a look at how it was done and look at the data too. So that was one of our original design goals. And as we went through it, the main objective here was we wanted to improve the accuracy. So after we did that neural architecture search, we had a smaller model, which was great, and we're able to get it back to the original accuracy. The next goal with the data sets was to improve the accuracy on essentially 5 or 6 domains. And a few of those were subsets of reasoning like math and coding and scientific question answer, as well as some of the non-reasoning tasks like tool calling or instruction following and chat. And so as we went about doing that, we focused on curating specific data sets to essentially boost the accuracy on those skills. And we did it in 2 ways. One was the first way, yeah,
You
perfect.
see the diagram?
Yeah, that's
I
exactly.
figured I'd put it up. I mean, it's such a good diagram.
Thank you. So the essentially under the supervised fine tuning category here, inside that box, we have reasoning on and reasoning off. And so we curated data, say for math and coding, for reasoning on and reasoning off. And we did that so the model would know how to answer simple questions like what's 2 plus 2? We don't need reasoning for it. So we curated that data. And then we curate more complex data, say like algebraic equations or word problems. And that way the model would also learn when it could reason, it could think through it and what that would look like. And in doing that, we leaned on a bunch of these great models in the community as experts. And so we used each of these experts for different domains. And so DeepSeek R1 we use for a lot of the reasoning, math, and coding. And then for non-reasoning, we use models like Llama and Quen, who are great at, say, like math and coding without reasoning, but also things like chat and tool calling. And we did that so we could try and blend the best, essentially the best skills from the models in the community together into one place. And so we did that all. And at the end of it, we've also published that data set. So it is up and available on Hugging Face. You can see the question answer pairs. There's, I think, around 30 million question answer pairs in there. So people can go pick and choose. They can use it and deploy it as they want. We actually, earlier this week, had a partner, ServiceNow, who announced a model, Llama Nemotron, where they took this data set and trained their own reasoning model. And they were able to kind of pick and choose which pieces they wanted to create the skills and things that they needed inside their company.
And I'll let you go through the rest, but I've got a question right there and then. Like, some people get worried about what kind of quality checks did you do on these 3 million pairs?
Yeah, and the quality is important. I think when doing synthetic data generation, there's a few stages to essentially you want to ensure high accuracy. The first is the prompts, like what seed data or how do you prompt the model? And then the second are the responses. As we went about doing this, we used a few techniques in here. So on the prompting side, we did think about focusing on prompting the models where we thought they would be strong. So for example, we use Llama for chat, but say we didn't use a reasoning model for basic math. And so it is important to think through essentially what are the models great at and make sure your prompts focus on those core skills. And then in vetting the responses, we did spend a bit of time going through, even on the human manual side of vetting some of them. And then I think going forward, we'll likely spend more time here with things like verifiers and reward models. We did a little bit of that, and you'll see that more to the right on the RL side. But I think there's a great opportunity to do a lot more there. And this is part of the reason we opened all of it, is we did want the community to spend time and think through this because there's a lot of nuance to it. And we knew at the end of the day, some enterprises, and I think ServiceNow is a great example, they have other goals. And so some of the data is useful and some of it might not be. And we wanted to make it all available so they could go through it and vet it themselves. We do have other things available like classifier models that can be used as well here. And we tried to publish some of those as well too, so people could see like, say, the content of news versus sports and those types of things. So they could also make decisions and essentially around what types of data blends you want to teach the model.
Perfect. Anything else you want to cover on this pipeline?
I do want to touch on the RL. So after the supervised fine-tuning stage, where essentially we were able to enhance some of the core skills. On the RL side, we were just getting started here with Llama Nemotron, and I think this will be a place we'll do a lot more in the future. But there was a few specific tasks we had an opportunity to spend time on running RL with. And what's exciting here is that with RL, we're essentially just bound by the amount of compute time that's available. And the more time we have, the better the model becomes at these tasks. And what we did in these stages is we found ways to try and automate asking the model a question, grading its answer, and teaching it about its grade and giving it a chance to try again. And so in these domains, I think you can see on the slide there, scientific reasoning, instruction following, and chat. Those are some of the domains. If you watch the leaderboards, you'll see that even as new models are coming out, we're still maintaining leadership in these domains, mostly because the RL is one of the best techniques to get to some of the best accuracy in the world. And so I think going forward, I'm optimistic we'll see more of this out in the community as well too, and hopefully more people talking about it and publishing the techniques and the data. And we've tried to do some of that on our side as well, and we'll have much more coming about this, I think, over the next 3-6 months.
You want to talk about the RL and the instruction following at the end, which you touch upon at the beginning of the conversation here, that you kind of cap it off this way.
Yeah, and I think what's exciting here is any place we can find a way to automate the feedback. And so in the chat side, we actually have a fine-tuned reward model that we published in the fall. And for those who might have followed along, in the fall, we actually had a Llama Nemo model as well that was top of the chat leaderboards. And that was because this reward model is an automated way for us to teach the original model, whether it's doing the right thing or not. And so it essentially grades the responses of things like helpfulness on a scale, conciseness, verbosity, groundedness, those types of things, and teaches the model how well it's doing when it generates responses. And there's a bit of work that goes into creating those reward models. We curated a data set we also published, training the reward model, and then spending time in this essentially this inference time kind of scaling loop here, where the more we run inference, the more feedback we get in the model, and the better it becomes at chat because it essentially learns it's generating responses. It learns these responses are less helpful. These responses are less grounded. Focus more on making them helpful or focus more on making them grounded. And giving that granular feedback per generated response allows the model to improve significantly, much more than, say, the supervised fine tuning, where it's generally a few passes through and there's not really a feedback loop. And the same with the instruction following. There's a verifier and a data set we're able to use here to teach the model you followed instructions very well or you didn't, try that again. And so I think going forward, we're excited to expand this to more domains. I think we've seen in the community things like coding and math. We've published some data sets on those since this model came out, I think a few weeks back as well. And those are some of the more popular trending data sets on Hugging Face as well too. So I anticipate this will be a place for growth in the community.
All right. So, one of the big innovations here, you touched upon it, but I want to put the finger on it, which is the whole reasoning on and off. The ability to toggle reasoning via the system prompt. I mean, that's very unique, and I'm sure a lot of people are going to follow suit on that. Um, and obviously, can you expand what was the idea with this, how you see it apply to AI agents and beyond, and the value, and also, what were the key challenges in implementing this?
Yeah, the reasoning on and off was one of our original goals at the beginning. We had seen that models in the community were either good at reasoning or good at tasks not reasoning related. And we wanted to make it simple for people to deploy just one model. And so we had to think through what was the best way to teach a model to know when to reason and when not to, and also make sure there was a control that enterprises who know their domains better than we do could explicitly make decisions and tell the model when to reason and when not to. The the motivation behind a lot of this is reasoning generates many more tokens, and so it can translate back to a higher latency and a higher cost. There are scenarios where it's super valuable and we can solve things we couldn't before, and then there's scenarios where we don't need it. And so we wanted to make sure enterprises had that level of control that they could to some degree determine how much they wanted to spend, say, answering a question with using reasoning versus not using reasoning and be able to kind of reduce the latency or the end user experience as well as the cost for them. And so those were kind of the design goals going into it. We didn't know how to do it at the beginning because we hadn't seen it done before in the community. So as we went into it, we had to think through what would be the best way to go about it. And the quickest way we could come up with was in the supervised fine tuning stage to just literally teach the model, here's one question and two ways to answer it, one with reasoning, one without. And so as we went through that exercise, to some degree, we doubled the data set to have to do that. But the end outcome is for the end user, they just have one model and they can, in the prompt, tell the model, use detailed thinking on or use detailed thinking off and gives them full control over it. But on the training side, we had to spend more time teaching the model how to do this. And I think what we have there today is kind of like a V1, so to say. It's the first iteration. I definitely expect others to follow suit. And things we're excited for in the future are how do we essentially time bound or token bound some of the reasoning? Are there some greater controls that we can think through how to give people? And I'm optimistic too to see more of this in the community going forward. I anticipate there'll be a few more breakthroughs here, probably over the next 6 to 9 months, because the problems we can solve with reasoning are great. It just comes at a trade-off. And I think that trade-off will have a lot of people thinking through how to make those decisions and how to do them more efficiently.
Yeah, and look, we all know like the rubber meets the road when we go to production, and production's latency, cost, accuracy and reasoning, but usually it goes overboard, right? And then it creates production issues, right? As people try to scale, latency goes crazy and so on. I love the flexibility here. I know a bunch of production use cases that will be delighted about this, saying I can just, for these type of questions, give me a 1 second response, like 3 tokens, and I think more about this one. Yeah, so it's terrific. So how did you think about, when you published this model, you talked about doing the trade-off between accuracy and efficiency. How do you, as you're building this model, you'll tell me how long did it take you to build this model, right? The team, and how do you know where do you put the compromise between accuracy and efficiency?
Yeah, it's definitely a challenge and a trade-off every time. When we set out, we wanted to do both, which is hard to do. And so as we went through it, we actually started with the super model, and that was our starting point, mostly because it was the most recent model in the community from Meta, the Llama 3.370B. So we started there because we wanted to get that accuracy. We weren't sure yet if we were going to be able to boost it as well as essentially reduce the model size. So that's where we started. And what we found is that we were able to boost the accuracy through all those training techniques and the distillation we did up front. So there's a little bit of trade-off here, the order of things. We did distillation up front and we recovered the base accuracy. We did publish that checkpoint out into the community so people could go see it, but we wanted to go a step further and add in reasoning and make it the best in the world at the reasoning scores. And so in doing that, that's where the SFT and RL came in. And those essentially took a bit more time with all the synthetic data generation because that data didn't exist. And so we had to go create it. And then as we went through the training, we spent time thinking through how many epochs we spent for each of those skills. And we measured the accuracy along the way. And in the end, we tried to balance through improving all 6 of them, as opposed to making it really great at 2 and average at 4. So that was kind of a trade-off. It took a bit more time for us to go measure all 6 and find the right combinations to get them all to increase. But we felt it was important to make sure those 6 scenarios in enterprise settings would be world class. And then there were things like I mentioned MMOU that we didn't spend time on improving and just tried to make sure that the model didn't regress or essentially forget the things it knew before we started. So it did take some priority and trade-off. I think in the end, though, those were the right categories for the enterprise customers. I think Chad and instruction following, those were the right things to focus on.
Okay, so obviously you're releasing this model family as part of the open source community. You've touched upon a bit like what some of the gaps you were trying to address at the beginning, and now we've talked about reasoning on and off, which are production gaps, and really unlocks to scale up production here. Is there anything you want to talk about how NVIDIA and your team thinks about and these models think about how they fit in the open source ecosystem or LLM ecosystem? And you're building around and with the Llama kind of base and so on, LLMs. Any thoughts about that?
Yeah, and we published models for a long time into the community, and I think with Llama, what we're excited about is the traction that they had with enterprise customers. And so, in all the great research NVIDIA publishes all over the place, all sorts of domains and content we're constantly putting out. What we wanted to do in this specific scenario was build on Llama's momentum with enterprise adoption. And we felt that there was a great opportunity to just be really narrow and focused on a few specific things because the Llama base model covers many things really well. And so we didn't feel like we had to go broad. We actually had an opportunity to build on top of them and be very focused. And I think with like LlamaCon and the events happening last week and the announcements they've made, it sounds great. And I think we're excited for Llama 4 and a lot of the work happening on there. And so going forward, we expect we'll continue to find some opportunities to focus on really specific things, while Meta does an incredible job at building one of the best general models that enterprises can put in production. So from our point of view, I think the reasoning we'll continue to focus on, and we're excited for Meta's work there as well. I think the tool calling, the instruction following, and chat will likely continue to focus on. Some things we're thinking about going forward are like multilingual, I think is a place that we want to spend a little bit of time on. There's, for large enterprises, there's lots of languages in the world and there's many models out there that do many of them great. There's probably just a few that we'll focus on and try and make sure we can have this best in the world accuracy for things like reasoning and tool calling and chat on a few languages. So that's probably the next big thing on the horizon that we want to expand to beyond the great stuff of model architectures. Llama 4 has a new MOE architecture we're excited about. So we're optimistic there's some opportunities there to also think about how to distill that architecture down as well and make it optimize it for specific GPU sizes from NVIDIA. So yeah, I think there'll be a lot of fun stuff happening there.
And when you're saying multilingual, you're talking 50 languages, right? Or 24 and like others have done. Is that what you're talking about? Or you're talking something different?
Yeah, I think we'll probably start, say, 5, 10 in that domain. The challenge we have is in the community, there's not great benchmarks for, say, reasoning or tool calling in a wide variety of tasks. And so as we're going about this, we're also having to create evaluation data at the same time as the training data. And so it's taking a little bit longer. If that had all been out there, this would be a little bit easier. But that's
Right.
why we're excited about it is we like hard problems. And so that's probably why the languages will be a little bit smaller to start, is we just don't see like a great breadth of it out in the community yet. So we'll have to do some of that along the way as we do it.
Okay, wonderful. All right, well, now we're going to talk about another model, open source model that you guys released that is state of the art, which is called Parakeet TD 06 billion parameters that achieve like a new standard, state of the art for automatic speech recognition, or what people in the industry call ASR. I usually call it ASR, just a bit mouthful, which transcribes 1 hour of audio in 1 second. 1 hour of audio in 1 second. It's 50 times faster than the other ASR models out there that are open source. And what's amazing is like not only is it fast, very, very fast, it's got only a 6% word error rate, which is important, right? It's the accuracy when you do something. And so it's really like amazing what you guys released. Anything else you want to talk about that model before we go into the how you guys did it? Like it's so good.
Well, I'll say that when you asked how long I've been here, NVIDIA's been training ASR models, I think longer than I've been here because they were when I got here. So NVIDIA's been in the space for quite a while. I think the open models we've also published many over the years. And so the teams that work on this are great. And they again try and do this balance of how do we improve the accuracy while also optimizing the latency and the throughput. So I think this is just the latest in a generation of models that NVIDIA has been able to publish.
Okay, well, it's going to keep going, I'm
Yes.
sure. All right, let's talk a little bit how you guys pulled this off and what kind of architecture you used. I understand that you used the model you utilizes a fast conformer architecture with some specific optimizations like 8x, depth-wise, separable, convolutional downsampling, and maybe also and you'll talk about it like limited context attention. And tell me how you guys got to this approach and why does it work and does it help just on speed and throughput or does it help on accuracy as well? Like or being able to process 1 hour, by the way, the elephant in the room here, it is 1 hour of audio that's also handled in one shot. So it's pretty impressive.
Yeah, yeah, and I think if you followed along, we've published a variety of architectures over the years, and Conformer is originally from Google, and they've done great work there. What we wanted to do with that Conformer architecture is try and make that more efficient and essentially faster without reducing the quality. So it's a great model architecture, and we've essentially done a few things in here, and I'll kind of walk through them and highlight them. So on the Conformer side, like you mentioned, the depth-wise separable convolution downsampling, essentially what we do at the beginning is on the input we're essentially sampling that, downsampling that input significantly so we can shrink it. And that helps cut how much compute we need to process the audio and reduce the memory as well. So that's kind of one of the techniques, I guess, here. The other one you mentioned, the limited context attention. What's exciting here is that by limiting the essentially we're focusing on smaller chunks and we're essentially able to overlap them. And by doing this, it allows us to keep the accuracy but provide a speed up. And then the third thing we've also done here, I'll mention, there's a few. On the attention side for the encoder, there's a sliding window attention technique in here as well, which people might recognize. I think we saw it in LLMs as well along the way. And so that allows us to get through larger audio files without having to split them into shorter chunks. So we essentially can see more in one pass. And then the other piece, beyond the conformer side of it, the TDT, the token and duration transducer. So on that side of it, what we've done is that there's essentially this kind of RNN transducer technology, and that would go one frame by one frame. And so what we wanted to do here is we've essentially been able to allow it to predict the tokens and how long it expects those tokens to last. And that allows it to make some decisions to skip over frames and speed things up. And so that in and of itself is around like a 1.5 to 2x speed up. So uh, there's all sorts of great stuff. I'll mention a few more in here too, but you kind of getting the gist here is that there's
No,
a
keep
lot of
going. And I want to go back to one or two of
okay.
them. So you,
Yeah.
those
So
are, those are amazing, frankly, right? It's like predicting, and we'll come back. We'll keep going. Yeah.
yeah. Another one that we have is what we're calling a label looping algorithm. And so essentially what we can do is that when we have to decode, like say we're running through a batch inference with the token and duration transducer, when we're running through that in this label looping, what we're doing is we're able to start advancing the tokens independent of other samples. And so we're essentially kind of like separating up the workflow there. And by doing this, it allows us to sweep and loop over frames and labels. And so we're able to kind of do an outer loop and an inner loop. And that allows us to get through the decoding quite a bit quicker as well, too. And then maybe the last thing I'll mention here is on the decoder side, we were able to move some of the decoder compute into CUDA graphs, which is a more efficient way to run many small kernels. And so that piece as well gave us around at like a 3x speed boost. So you can see that kind of like all of these in using like at the end of this TDT models, we're able to make them about as fast as CDC decoders, which are also quite common, but we're able to bring them up to a higher accuracy level. So we're kind of always trying to balance this. Can we speed it up without reducing accuracy? And there are other techniques like CDC decoders that have been around for a long time that are really fast, but maybe not as accurate. And so it kind of depends on the scenario, but you can kind of see the theme here. We're trying to balance both of them in these speedups by keeping the accuracy as we go about it.
Can we go back to the limited context attention? Do you think, which is one of the, I don't want to say techniques, skills, approaches, architectures that you use, do you think this will apply to more opportunities down the line?
Yeah, I think so. And like the patterns, even like the sliding window attention, you see
Yeah.
things used other places too. And so the teams, there's a lot of experiments. So they're constantly what we're trying to do is find techniques we see elsewhere, come up with new techniques and try and apply them. And so, on our side, actually, some of the researchers who work on this actually work on Llama Nemotron. So we have smart people working across both of these. So I do expect that some of these techniques will be used more places going forward as well, too. And I think, like in terms of uh, going forward, I do anticipate that like the TDT, the token and duration transducer, we've worked on that for a while, so I expect there'll be more improvements coming forward on that. And the conformer architecture we've been working on for a few years as well too. So I don't see these things going away anytime soon. I do think we will continue to improve them.
And do you think the TDT, do you think what do you think is the other applications where this could be used in other domains?
That's a good question. I'm not sure that if I see this one going too far outside of it. Like the history of this is more based on like RNNs and RNN transducers, which we've mostly seen used in ASR. So I don't know if that one will generalize as well. Some of the techniques we brought to it, like using CUDA graphs, that's a general technique that we use whenever we see bottlenecks in kind of like a pipeline of kernels running in a model. So that technique we do bring lots of places, and we brought it here for the decoder. I'm not sure though how much TDT will translate out to say other domains like say large language
It's just
models.
so elegant.
Yeah.
So elegant. Seriously, right? Simple, elegant. All right. So, of course, we're going to talk about data, AI data. It's got to be at least one question on AI, right? So, the question is like, how do you obviously you got to have a big data set. It's got to be diverse. How do you ensure that the data that is in this data set enables to have a model that's pretty robust, that can handle accents, dialects, maybe vocal range, pitches, and even noisy background conditions and so on, which tend to mess up the outputs, right? How do you ensure that with the data set or maybe other ways. Maybe I don't know.
Yeah, no, you're right. When we think through this, it's interesting. Like as people, we don't really spend too much time thinking about it. We hear accents, we hear background noise, and we just have learned to how to filter them out or how to understand them. I think with the deep learning models, the challenge is the model is only as good as the data it was trained on. And so when we started this many years ago, kind of the challenge was the model. If we had limited data, say for an accent or for a language, the models just weren't great at it. And so these originally they felt like edge cases, but they become more and more common over the years that we just kind of expect the model can understand 100 different dialects of English, and that's just how it should work. So we've had to spend quite a bit of time modeling the data set after that as well too. And so as we go through that, we use things like classifiers, and we go through and we run through our data set, and we try and get distributions on what types of accents are represented there, what types of dialects, the things like noisy conditions. We have customers. I think at GTC we mentioned Yum Brands as a customer, and they have like a drive-through use case, and you can imagine like highway background noise. Like there's all sorts of crazy stuff, and so the challenge is making sure we have the right blend and distribution of that in the data set. So when the model encounters background noises, it's able to accommodate for them. And so that's why a lot of it depends on the quality of the data set. I think one thing I do want to mention is we do plan to open a lot of the data that we've used for this model, the Parakeet model at the top of the leaderboard. And so I think we're expecting something like around 100,000 hours of data we'll be able to share with the community where we've gone through and done all of this essentially curation.
Yeah.
And you can see in there things like looking at, sound to like SNR levels, noise ratio levels, background noise. We've thought about things like telephone formats for things like call centers where the audio gets downsampled. So we've tried to include all of that variety in the data set. So the model can be good in all these different places. Because what we realize is people use the model and they'll use it in a call center, they'll use it in a drive-through, they'll use it in all sorts of places. And we wanted to have as large of a representation we could of these kind of enterprise scenarios that we were seeing people use it in.
All right, super. And this perfect lead way into my last question around the Parakeet. The Parakeet family currently has the 600 million parameter model and the 1.1 billion parameter models. How do you guys think about future development and with the Parakeet ASR kind of family of models, and where is this going? And what are maybe different directions, or how do you think about this?
Yeah, we're thinking of maybe two different dimensions here. So one is the size, and the other is the number of languages. So in terms of size, we're going to try a larger one and a smaller one. So we kind of went in the middle for this first release to show what was possible, kind of like how I mentioned with Llama Nemotron Super. So we usually try and start in the middle and prove it out. We plan to go a bit larger, probably around like a 2 billion model, and we expect we'll be able to handle more languages and more dialects in there. So that's what we'll be testing out at the larger end. On the smaller end, we're thinking even down to say 50 million, we're going to try. The reason we're thinking that is at NVIDIA, we do have the Jetson Orin line. And so they have scenarios where there's a smaller footprint that they need to run at the edge. And so we're trying to think through what kind of variants that could fit in there. So these could be things like enabling robots to hear in real time in noisy places. And so we're going to try and figure out what would be the right kind of trade-off there. So I think that'll be something to look forward to. I think some other things in terms of just technology, I think we mentioned the TDT, on the TDT side, we plan to work on streaming. And so today, a lot of the work has been like on kind of this offline batch, but we want to think about streaming scenarios where it needs to be live in real time. And I think I mentioned the data set, so we're excited about being able to publish that. And then maybe the last thing is if people are using the models and they want to put them in production, probably the first place to start is using word boosting. And so we do have some great capabilities in the model of being able to modify things like, say, text normalization, where they could put in domain-specific terms or acronyms, those types of things. And so I think there's kind of a wide variety of options here for people as they want to get started or they want to experiment with these.
Yeah. By the way, I'm going to ask a question here. So I'm very familiar with NVIDIA Orin platform. These models currently, either one would run on the NVIDIA Orin?
I think that probably the 0.6B would. I would need to double check, but I would think it does.
I think it would, right? It's
Yeah.
small enough. It probably would, right? Inverter Orin packs a punch. And and so I really love your use case about the robotics. I just want to double click on that one. I think people have been focusing a lot on the robot seeing, but hearing is also quite important. And the other, right, and this, I just want to, I'm just putting the story together here. The other thing is robots, they need to respond very quickly for safety reasons, because if they're slow, something could happen. And so what do we have here? Like a model that's 15 times faster, responds really quick, understands really quickly another modality. So I think that's like a slam dunk.
Yeah, and the reason I hesitate a little bit is like on the robotic side, there's lots of other models running, like you mentioned, and so we
Yeah,
have to
that's right.
go a little
I
bit.
didn't say multi-modal. I said
Yeah.
one.
Yeah, and so we think a lot about Parakeet and ASR, but we do realize we're sharing compute, and so I think that's why going
I didn't
forward.
say sharing compute.
Yeah, yeah, yeah. Yeah. Well, I think like going forward, the reason we're thinking about trying to shrink the model is we want to make sure that there's lots of things have to run concurrently. And to your point, if somebody says stop or don't go there, it has to happen right away. We have to interrupt and be able to do it. So it is really critical that they can hear in real time and we have that low latency.
Okay, yeah. So as you come out with smaller versions, then they'll be the ones that can do sharing compute. I totally do agree. It's multi-modals on these Orans, but they could have two Orans as well, right?
Yeah.
That's the other way, right?
Yeah.
I've seen that. Perfect. Anything else you want to add? We're going to open it up about, we've talked about the Nemotron. They're both open source. They're both state of the art, basically. They're both very fast, high throughput, very cost efficient. They basically run on a smaller footprint. I mean, that's also right, the benefits. Anything else you want to open it up? This is sort of the one last topic here.
Uh, I think that's a great recap. Those are kind of the three things we set out to do. So we wanted to get state-of-the-art accuracy and show people it's possible. We wanted to try and optimize the footprint so we could fit the right GPUs in terms of latency and throughput. And we wanted to get this out in the community and open all this up. So we've tried to be, as friendly as possible in getting data sets out there and getting the right licenses around things and enabling people to go try it out. So I think we're looking forward to the community and feedback and people building derivatives and trying new things on it, and we look forward to learning as well.
And maybe we'll top it off. Like, where are all these models available?
Yeah, everything we've published is on Hugging Face. So all the models are there, the data sets are there. The software stack to run them comes from NVIDIA. So we have all of that on either NGC, and NVIDIA is essentially content repository. Oftentimes, though, a lot of the software is open source, so it's all on GitHub as well. And then there's things like pip wheels to make them easier to install. So a lot of it's under Nemo is kind of the key home for a lot of the software stack if you want to run them or if you want to fine tune them and improve the quality of them. Those would be the best places to get started.
Yeah, and it's pretty much plug and play.
Yeah, yeah, we've tried to make it as easy as we can. We use that same software to build the models ourselves, and that way, it should be pretty easy for people to pick up and deploy it as
Yeah, it's
well.
all optimized. Wonderful. Well, Joey, this has been great. I'm amazed how NVIDIA once again just gives back to the community state-of-the-art models that will end up in production. So this is terrific. Thank you so much, and look forward to next conversation.
Yeah, perfect. Yeah, thank you for the opportunity.
Thank you. Take care, Joey. Bye-bye.